Please like and subscribe to this channel and press the bell icon to get new video updates.
Говорит Москва.
A radio broadcast receiving solution for a very different nation from ours. There was a problem before the 1970s. Vast areas of the USSR were without electrical power distribution. From the 1930s, the government wanted all citizens to be able to receive state radio broadcasting, either by local radio receivers or via wired systems of loudspeakers driven by neighborhood and apartment block central receivers. In fact, these wired speaker systems serviced more citizens before 1953 than via individual receivers in homes or workplaces. As you might imagine, the objectives were to indoctrinate Soviet citizens about the USSR version of communism, distribute their versions of news and education, promote Soviet culture, and provide music and entertainment. Without an extensive AC mains network to power radio receivers, what are the options? Dry battery power. The downsides: recurring cost of replacement of batteries. Low and high temperature conditions limit performance. A proven record of a managed economy unable to maintain reliable supply chains for consumer products. Local generators powered by fossil fuels. The downsides: expensive to make and requiring constant maintenance within a system with chronic inabilities to maintain reliable distribution of parts and refined fuels. Wind power charging batteries. The downsides: winds unreliable throughout the year. Many areas with harsh weather disabling generators. Battery charging maintenance schemes not as sophisticated as now. What are alternative methods for producing small quantities of constant electrical power? Scarcely any that would service the majority of their needs. One method, first discovered in 1821 by Seebeck and correctly explained by Ørsted, who named it a thermocouple a year later, was a junction of dissimilar metals that, when placed on a source of heat, will produce a voltage difference at the cool ends of the metals. This voltage difference is very small, on the order of a few microvolts per degree C. These thermocouples can be connected in series to produce higher voltages in an assemblage named a thermopile. The size of the junctions can be scaled to deliver a greater current, but energy conversion efficiency remains well below 1%. There was little practical use made of the Seebeck effect in the 19th century, the most work having been done in attempts to make thermopiles to provide low voltages for electroplating over hours at a time when practical small dynamos had yet to be developed. From 1890, thermocouples had been characterized sufficiently to serve reliably to drive galvanometers and later D'Arsonval-type meter movements for measuring industrial and chemical process temperatures. The first attempts to generate enough power to operate a radio receiver come in the late 1920s in Great Britain. These generators used elimination gas to fuel the burner. Using only thermocouples fabricated from various metals and metal alloys required an inordinate number of junctions to provide voltages high enough to operate vacuum tube receivers. Indications are that these generators were produced in very limited quantities with only a few surviving in museums. I know of no other attempts in the 1930s to market such a generator to power broadcast receivers. In the middle 1930s, the Ukrainian-born academician and physicist Abram F. Ioffa is credited with pioneering investigations into the properties of semiconductor materials such as zinc antimony that, when bonded to copper-nickel alloys, could produce thermocouple junction potentials of about 55 millivolts in production generators with conversion efficiencies below 4%. The first claimed use of this technology in Soviet industry was during the Great Patriotic War. A small 1 or 2 tube earphone-only radio, probably of the space charge variety, was supplied to partisans. The generator consisted of a metal pot with an array of semiconductor junctions bonded to the bottom of the pot, the pot being suspended over a fire. The pot was filled with water and became the cold side of the thermopile junctions. Before World War II, broadcast radio production in the USSR had been very limited. Following the war, decisions were made to develop various reference designs for broadcast radios that could be manufactured in quantity. In 1949, Alexandrov Radio Factory engineers were tasked with development of the ARZ-49 battery-operated, very low-power receiver with loudspeaker. Designed around the USSR's first miniature vacuum tubes, in Russian slang called finger lamps, they had reverse-engineered RCA 7-pin miniature tubes. The tubes had been provided to the Soviets during World War II through a Lend-Lease program. These tubes were contained in samples of the Galvin Manufacturing Company, Motorola, designed BC-611B handy-talkie used for short-range military communications. As mentioned before, reliable distribution of dry batteries, or reliable wind charger systems, was certainly recognized as a substantial problem. Professor Ioffa had earned great influence in informing government planning and was convinced that a thermoelectric generator could be developed to power small radios requiring only 2 to 4 watts power. Cost of operation would be very low because it could use only the waste heat of an oil lamp. By 1953, the first iteration of these generators, the TGK-3, was available for production. These first versions of the generator had 2 banks of thermocouples. One supplied 1.2 volts at 300 milliamperes to light the tube filaments. The other bank of thermocouples supplied about 10 to 12 volts to power a mechanical vibrator-type DC to DC converter, delivering about 90 volts at 10 milliamperes. The delicate DC to DC converter was something of a reliability issue and certainly added considerably to the initial system cost, but it worked well enough and some thousands were manufactured. There was another incentive to develop these generators. The communist model, with thousands of farming, mining, and forestry collectives, covered large areas without wired communications. They developed low-power two-way radio telephones. A claim of some 70,000 Harvest Series two-way radios were made over 10 years, some percentage of them being powered by this thermoelectric generator. A slightly larger version generator, 10 watts, and converter with added storage battery to source the peak load of the transmitter in talk mode. Articles in Radio Magazine discuss theory of design but give no descriptions of manufacture. That was a state secret. In 1956, they had perfected a method of making high-density series slabs of thermoelectric junctions that could be assembled into bars producing about 10 volts. 10 of these bars would provide 90 volts directly, thus eliminating the considerable expense of the DC to DC converter. My example is never going to power a radio again. The design life of these generators was said to be 5,000 to 7,000 hours, which was considered to be 5 or more years of normal use. This example is heavily corroded by many hours' use. Poor assembly of my 1958 model TZGK 2.2 allowed combustion gases to get to slab connections. But I had to give it a try. Maximum output when heated with a 1,000-degree heat gun was about 10 volts at 2 milliamperes, just enough to light one small white LED. But my generator is entirely suitable to be cleaned, painted, and placed on exhibition. You certainly would not be burning this lamp on exhibition. When given to me by a collector friend, it was complete but badly corroded and not at all presentable. This lamp is fitted with a tubular argon-type kerosene burner. The steel and brass stamped parts are swaged together and in different states of deterioration. I judged it impossible to properly replate the assembly. The font had 2 small pinhole leaks. I repaired them for cosmetic reasons. Some of the later fonts were painted with aluminum, but there was just enough remaining forest green enamel remaining on this font to identify my unit should be painted forest green. I had to locate proper-looking stamped brass chain that I finally learned is called Windows sash chain. A local custom sheet metal shop helped me to recreate a proper flue pipe to replace the heavy piece of aluminum scrap pipe. A thick asbestos bushing between the top of the clear glass globe and the bottom of the generator was replaced with safer ceramic fiber blanket material. All other asbestos at the base of the radiator fins was saturated with clear acrylic resin. The original plastic insulated wire looked terrible, but cleaned surprisingly well. The little round box houses 3 receptacles that mate to the radio's existing battery cable plugs. I note that in recent decades, a very few new old stock generators have been found in South America, Southern Africa, and former Eastern Bloc European countries. When they do show up, prior to 2008, they were trading in the range of $800 to $1,200, certainly out of my price range. Now that I had an authentic generator designed to substitute for standard dry batteries, I wanted to find an appropriate 1950s USSR-made battery-powered broadcast receiver. From 1950 until 1963, there were a total of 12 Soviet-made radios that could be powered by these generators in place of dry battery blocks. Thanks to collector Barry Etheridge in Georgia, USA, I acquired an Iskra 53, this one built in 1958. Just to set the mood a bit, I'll give you a 50-second sound clip from a fascinating 4.5-minute long color propaganda film of 1949 that you can see on YouTube. It is titled The Harvest Song. I think it appropriate for a radio designed for remote Soviet regions.
Somebody
This is essentially the Iskra 49 limited production radio with a new molded phenolic, aka Bakelite, cabinet. With the back cover removed, you see a chassis of a little 4-tube superhet receiver, an IF transformer that looks a little bit odd. I prepared to remove the chassis for inspection. I unsoldered 2 wires going to the loudspeaker voice coil, removed the chassis, and prepared to unsolder the soiled battery cable for a proper cleaning. But I touched the soldering iron tip to one of the cable connections and nothing happens. No melting of the solder at all. A closer inspection and I realized that 100% of the chassis component and wire connections are welded. The little inset picture shows how the wire leads were prepared before applying the welding electrodes. I found a few Russian collectors online, all under 40 years old, that tell me that there were at least 2 broadcast radio receivers and 2 television receivers that use welded connections. They understood this to be a way of connecting circuits in cheap, i.e. third-class products. But some detective work indicates otherwise. In the early 1930s, the government of Germany fell under the control of the Nazi Party led by Adolf Hitler. A high priority was placed on rebuilding the German military. This required some raw materials not found in the German homeland in commercial quantities. One of these was tin. Germany got most of their tin from South America. It was evident that at war, those shipping routes could be blockaded. 2 companies in Germany began to study how to weld small electrical wiring and components. By 1942, some percentage of German military electronics were being welded in order to conserve a scarce commodity. The techniques found use and even preference to conventional solder, especially in production of avionics, aircraft engine control and monitoring, and very importantly, operation of rocket bombs like the V-1 and V-2. The Western Allied powers, of course, wanted to learn as much as possible about technology of the German war machine and already had functional military agencies such as the Enemy Equipment Intelligence Service analyzing their methods by 1942. There were interrogation and recruitment programs for captured personnel under Operation Overcast, later named Operation Paperclip. The Soviet Union was operating their own similar agencies as the Eastern Front fell to the Red Army, and they managed to secretly organize a stunning event, Operation Osavakium. In the early hours of October 22, 1946, they loaded some 2,500 engineers and specialist workers of the former Nazi war machine, headed to various Soviet territory installations and factories, along with some 4,000 family members. It would be 10 years before some of these people had the opportunity to return to East Germany. This included a massive operation to transport from Red Army-held German territory as much related manufacturing equipment as possible. Much of German military technology was superior to that of the Soviets, so they simply began building, in many ways, copies of German equipment. Soviet workers had to receive new training and acquire new skill levels to execute these German designs. They had never used these considerably more difficult wire welding techniques for electronics going into aircraft, rockets, jet engines, etc. What better way to hone their craft and then identify the best workers for the task than with months of practical work wiring cheap broadcast radios and televisions before assigning them to work on high-value military equipment. Making repairs around defectively welded circuitry was far more difficult and time-consuming than conventional tin-lead soldered junctions. They needed people that could get things right the first time, every time. Let's take a tour of this power-thrifty little broadcast receiver with welded circuitry. The Iskra 53. The Russian word Iskra means spark. A perfect name for a welded radio, don't you think? First off, like many European designs, it was deemed necessary to tune both the long-wave and medium-wave broadcast bands. The Soviet-made finger lamps were often direct copies of the RCA 7-pin miniature tubes. In later years, these tubes would even have the equivalent USA markings like 1R5, 1T4, etc., in addition to the Russian nomenclature. But however, not all their miniature tubes were electrically equivalent. The superheterodyne intermediate frequency was 175 kHz and was tuned using threaded ferrite slugs. In order to obtain the most power-thrifty operation down to the minimum specified B battery output of 60 volts, required that they use a clever circuit consisting of a third winding on the audio output transformer and copper oxide rectifier to provide a tracking grid bias dependent on the volume levels of the audio content. The two dry B battery blocks each have an 8-pin receptacle. Note that the receptacle has two keys in the center of the receptacle. When new, the battery cable plugs are inserted so as to deliver 45 volts. When the battery discharges down to 30 volts, the plug is rotated to the other receptacle position, connecting an additional 15 volts to the string. Note, there are two chassis-mounted pin receptacles in parallel with the plate circuit of the audio output tube. I'll explain shortly. A side note is that this tube does not have an electrical equivalency to any RCA tube design. Resistors are exact copies of Siemens products circa 1940. Capacitors, both electrolytic and paper dielectric, are also essentially German copies. Note the two gimmick small-value capacitors. Excess insulated wire is wrapped around a copper wire post to bring a circuit to peak resonance simply by pulling off some of the wire and clipping. Note how the various RF and IF coil bobbins are glued directly to a phenolic board. There is absolutely no opportunity to repair these parts. Certainly another reason for the workers to be trained to get the job done the first time, every time. I mentioned the two connections to the primary of the audio output transformer. You might have expected those pins to be marked as connections to a remote loudspeaker, but no. This is where you could use your radio loudspeaker to connect to the local wired radio distribution you may have had in your apartment or workspace. I'm not aware of any other nation to have a significant program to apply thermoelectric generators to operate vacuum tube broadcast radios. Professor Aofa served later as a top atomic scientist and administrator. This led to projects to develop thermoelectric generators using radioisotopes as heat sources, used for such things as powering automatic lighthouses, meteorological stations, and radio relays. After the dissolution of the Eastern Bloc in 1991, many of these nuclear thermopiles were simply abandoned at the end of their service life. There was great international concern about the possibility of the leftover nuclear material being used in so-called dirty bombs. There were international agreements signed to methodically decommission these units, but soon the program fell apart. As far as I know, there is no credible accounting of whatever remains.
Please like and subscribe to this channel and press the bell icon to get new video updates.